In this video I'm going to discuss how we can take percent compositions by mass and figure out empirical formulas for substances. An empirical formula is the lowest ratio between atoms that make up the compound. So for example, if I had something like C6H12, that's a 6, doesn't look like a 6, its empirical formula would be the same thing stated in the lowest ratio. So that's a 1 to 2 ratio in its lowest ratio. For ionic compounds, this term is a little bit meaningless because remember, ionic compounds are always written in their lowest ratio. But for molecular compounds, what it means is if you had a molecule, maybe N2O4, what is the lowest ratio between those atoms? What we're really trying to build towards is being able to find out what the molecule of a substance looks like based on its percent composition. But step number one is going to be finding its empirical formula, or finding the simplest, lowest ratio. Here's a set of steps. We're going to follow them. We'll sort of talk through why they work. And I don't know, I might come back and do another video that explains exactly what's going on here, or we might just sort of do this from a procedural standpoint right now and just sort of get used to doing it. So given a percent composition, we can work backwards to find the empirical formula, the lowest ratio between the atoms that make up the molecule. Again, lowest ratio, right? So if this was 2 to 4, the lowest ratio would be 1 to 2. These are the empirical formulas. The circle ones are the empirical formulas. What we're going to do is to convert our percent compositions into mass, we're going to assume 100 grams. That'll allow us to change the percentages to masses. So, for example, we see in this first example, we have 81.8% carbon. If we assume 100 grams, then what we can say is instead of 81.8%, that's 81.8 grams of carbon. We're going to find the moles of each substance, so we're going to convert that mass into a number of particles instead, since that will allow us to compare the number of particles. Then we're going to end up with some funny ratio that we don't like. So we're going to divide all of them by the smallest number. And then we're going to try to figure out how to get a whole number ratio out of what results from that. And I'll talk to you about what that looks like in a second here. So step number one, assume 100 grams. So just for the sake of right now, we can write that out. Assume 100 grams. And just to be clear, that means that our, let's just do for carbon, I'm only going to write this out once because we don't normally have to do this. Percent carbon would be equal to the mass of carbon divided by the mass of the total. So if I assume the mass of the total is 100 grams, and I assume that the carbon is 81.8% of the sample as discussed. Remember, when I use percents in calculations, I have to convert them to decimal places, so 81.8% is 0.811818. So that means the mass of my carbon is going to be 81.8 grams. So again, if I assume 100 grams, then my percentage can change into a gram directly. Here's the calculation Y in case you don't see that, but from now on I'm just going to assume that's the case. So this is my carbon, these are going to be my masses, and if it was 18.2%, based on everything I just said, I assumed 100 grams, so that's 18.2 grams of hydrogen. Now what I want is I don't want a ratio of masses, I want a ratio of moles or particles. So I'm going to divide both of these by their molar masses. The molar mass for carbon is basically 12 grams per mole. For hydrogen is basically 1 gram per mole. And so for my number of moles of each, I'm going to get 81.8 divided by 12 is 6.82. I know I'm going to get funny numbers here. I'm not too worried about that. And obviously 18.2 divided by 1 is going to be 18.2, so I don't have to type that out. Now I've got some funny numbers here that aren't helping me that much, because what I really want is I want a whole number ratio between these numbers of particles. So this is where these two tricky steps that I was describing are going to come in. I'm going to divide both of these numbers by the lowest number. So here 6.82 is less than 18.2. So I'll divide both numbers by 6.82. So this one obviously turns into a 1. And 18.2 divided by 6.82 is 2.67. So that's not great. I wanted that to be a whole number ratio. So what I'm thinking about here is when I look at this division part, what fraction gives me a division that looks like that? So if it had been 0.5, then hopefully you would recognize that's related to, oops, what did I do there? Hopefully you would have recognized that's related to 1/2. If it had been 0.25, hopefully you would have recognized that that's related to 1/4. Here I have 0.67, and hopefully you'll remember that's related to 2/3. The other ones that I'd expect you to recognize is 0.33, which is related to 1/3. And the last one, 0.2, which would be related to 1/5. Anything that's more complicated than that, then I wouldn't expect you to remember. So this 0.67, maybe the reason that that resulted was because I had a 2/3 at some point that made that 0.67 for me. So if I don't want a 2/3, I don't want that 3 on the bottom, then I can multiply both of these numbers by 3. This one will turn into 3, obviously, and 2.67 times 3 turns into 8. So by multiplying both these numbers by 3, by recognizing the fraction that caused that 0.67, then I can get this back into a whole number ratio. Here my empirical formula would assume that I have 3 carbons to 8 hydrogens. So let's run through the steps again and try and discuss why we did each thing. Assume 100 grams. That's just so we can convert our percentages to grams. Find the mass of each substance, so that's what we did. Find the moles of each substance. So that's the mass, but remember the particles of these substances don't weigh the same things, and we want to compare particles to particles. So we have to divide by how much each particle weighs so we can get moles, or really what we have here is the number of particles, right? Just a representation of that. Now I know that I have 6.82 particles this for every 18.2 particles of that. But remember, when we're doing this, our empirical formula is supposed to be that ratio as stated in whole numbers. So 6.82 to 18.2 is sort of, it's right, but it's not what we need as a representation for the ratio between those two things. So here's the trick. First of all, we're going to set one of them to 1. So we'll divide both numbers by the lowest number. That got me 1 to 2.67. If this had worked out to like 1 to 5 or something, then I would have been done and happy. I would have said C1H5, and I would have been very happy. But it worked out to something funny. It worked out to 1 to 2.67. So it didn't work out into a whole number ratio, even though I did what I said to do in step number 4. So step number 5, I have to look at the numbers carefully, and I have to decide what's causing this decimal place. Here's my list of things to look for. If it had been 0.5, I would have recognized that it was a 1/2 that was causing it. If it had been 0.25 or 0.75. It was a 1/4 or 3/4 that's causing it. 0.67 is a 2/3, 0.33 was a 1/3, and 0.2 would have resulted from a 1/5. Then I want to multiply out whatever fraction is hidden within this number. So since 0.67 was related to 2/3, if I multiply both numbers by 3, then I will get rid of this 0.67. I will effectively multiply out the fraction that was hidden in the number and get up to a nice whole number ratio that I can then use to write my empirical formula. Sounds like we should do one more. A compound is 42.1% sodium, 18.9% phosphorus, and the remainder is oxygen. sodium, phosphorus, and oxygen. I'm going to assume 100 grams. So then for sodium, that means I have 42.1 grams. For phosphorus, I have 18.9 grams. And for oxygen, I don't know what it was. But if I had 100 grams total, less 42.1 for the sodium, less 18.9 for the phosphorus, how much am I left with for the oxygen? $39 grams of oxygen. Now I'm going to divide each of these by their molar masses. So this one, to get into, that's a mass. So I'm going to divide by the molar mass to get into a number of particles. So that's a 23 grams per mole. 18.9 phosphorus is 31 grams per mole. And oxygen is 16 grams per mole. 42.1 divided by 23 gets me 1.83. 18.9 divided by 31 gets me 0.6061. And 39 divided by 16 is going to get me 2.4375, whatever. So now that's the actual amount of ratio between the number of particles of phosphorus, oxygen, and sodium. It's useful, but it's a little annoying because it's not in a whole number ratio. So to get into a whole number ratio, I have to play those games again. I'm going to divide by the lowest, which happens to 0.61. And then I'm going to get 1.83 divided by 0.61, 3. Obviously 1. 2.4375 divided by 0.61, 3.99. That's close enough to 4. Okay, if it's really close to the number, then you can just give it a little bit of a round there. Okay, so look at that. I don't have to do step 5. I don't have to look for these annoying fractions unless they pop out. If they don't pop out, then great, my problem's done. 3 sodiums, 1 phosphorus, and 4 oxygens. So that is my empirical formula for that compound. So, assume 100 grams. Find the mass of each substance by recognizing that a percent can be converted into a gram if I have 100 grams. The calculation showing that's here. Find the moles of each substance. So get out of mass and get into the actual number of particles, because that's what we're trying to compare in a chemical formula. And then look for decimal places that really represent what fraction caused that decimal place. Multiply out by the denominator, 3, 4, 2, 5, depending on what it is. It could be something worse, but we won't deal with that because this is enough this is a big enough list of decimal places to try and remember. And then you have your empirical formula. You have a whole number ratio between your number of each kind of element. If it works out to a whole number ratio without doing any multiplication, great. You get to skip number 5, step number 5. So that's how you find the empirical formula.